Welcome to Maths with EJD. We are still talking about numerical analysis, and our focus has been on interpolation and approximation. And we've considered quite some techniques like Lagrange polynomial interpolation and Newton's divided differences interpolation. We've also seen spline functions and cubic splines, which guarantees smoothness as we join points together. So here we are considering least squares approximation for linear fitting. And straight, of course, the idea is to understand and apply the least squares method to fit a linear model y equals mx plus b to a set of data points and derive the optimal values for the slope m and y-intercept b. That's the essence of what this is about. So introduction to linear fitting. Linear fitting. Okay, so linear fitting, also known, also called linear regression, is a technique used to model the relationship between two variables by fitting a straight line to a set of data points. The general form of the line is given by y equals mx. Y equals mx plus c. Okay, where y is the dependent variable. So that means y depends on another variable. We have x, which is the independent variable. That's the variable upon which y depends. Y is the dependent variable. X is the independent variable. Then we have m, which is the slope. M is the slope, which represents the rate of change of y with respect to x. Okay. Then we have b, which is the y-intercept. Y-intercept. That is the value of y, the value of y when x is equal to 0. So that's some kind of base value or baseline, depending on the context in which you want to use that. So the least squares method, which we are focusing on, the least squares, as the name implies, least squares. The least squares method finds the values, it finds the values m and b that minimize the sum of the squared errors, the sum of the squared errors, or what you can call residuals, between the observed data between the observed data, between the observed data points and the predicted values. From the model. Okay, now let's see something crucial, which is the objective. What is the objective of least squares? So given a set of data points, call them xi, yi, we aim to minimize, the following cost function, which is the sum of the squared residuals, which is the sum of the squared residuals. So see what we have. That's j into mb. J, which is the function of m and b, is the summation from I equals 1 to n of yi minus that line now, mxi plus b. So you can see that this is actually what we started with, y equals mx plus b. So this is the generalized form of that. So yi equals yi minus mxi plus b, all this squared. So that's where the square thing is from, least squares. So now where yi is the observed value, that's the data points we have. Yi is the observed value of the ith data point. Okay, then we have mxi plus b. Mxi plus b is the predicted value, for the ith data point, based on the model, So the goal is to find values of m and b that minimize this function, that minimize this function. Okay, so let's look at the steps we need in this situation. Steps to minimize the error function. So the first thing is to compute the partial derivatives. Compute the partial derivatives. So to minimize the cost function, we first take partial derivatives of j, m, b with respect to m and b, then set them equal to zero to find the optimal values of M and B. So the partial derivative with respect to M is partial J, partial M, which is equal to, we are differentiating this expression with respect to M. So you see M is somewhere here. So it means it's under this bracket. So we have to bring down the power. Then M here is attached to minus xi. So you're going to have uh, bring down the power, differentiate inside where you get xi. But of course, negative. So you're going to have minus 2xi into the rest of all that. So let's see how we write that. So partial J partial M is equal. Okay, I said partial, not D. So it's partial J partial M. So partial J partial M, because J is a function of both M and B. So we have minus 2, which is constant summation from I equals 1 to N of the xi that comes out from the side of the M. Then what we have there, reduce the power. So that's function of a function. I think I talked about that a lot when I was under the basic calculus playlist, under differentiation, a function of a function. So if you have something like that, bring down the power, that is this 2 now, differentiate with respect to the M you're talking about. If you differentiate mxi with respect to M, you get xi. That is why the xi is out there. And the negative sign is because you have negative sign, because you have this negative sign right here. Okay, like that. Because if you open that up, you're going to have minus mxi. So if you differentiate it with respect to M, you get minus xi. So that's why you have minus there, and this is xi. Then minus mxi plus b. Now the power is 1 because bring down the power, differentiate inside, reduce the power by 1, and that's what you have now. So this is partial J, partial M. Okay. Then we have the other one. Okay, so we have the other one, the partial derivative with respect to B. So partial derivative, the partial derivative with respect to B is partial J, partial B, and that is equal to, so let's go back there. Now our focus is on B. Now you see B, so if you open this place up, it's more like you have yi minus mxi minus b. If you open up this whole place, so that to differentiate now, again, bring down the power, then differentiate minus b with respect to itself. So you get minus 1. So that's why you're going to have minus 2. This time around, x is not following. So that's the only difference. There's no x is not coming out, but you have minus 2 coming out. Because this 2 will come, then the minus beside b will also come. But then there's no other thing attached to that. So we are going to have minus 2b into all of that. So the jdb now is minus 2, rather. I said minus 2b because differentiate b, it's 1. So minus 2 summation from summation from I equals 1 to n of yi minus mxi plus b. And then the power is still 1. The power is now reduced to 1 again because we have differentiated like that. So that is the first step in this place. Then we go for step 2. That's step number 2. So step number 2 now is to set the partial derivatives. Set the partial derivatives to 0. Set the partial derivatives to 0. So by setting the partial derivatives to 0, we obtain the normal equations. We obtain the normal equations. So, and these are summation from I equals 1 to n of xi into yi minus mxi plus b equals 0. Of course, that's when you set this one to 0, you can divide through by -2, and because it's constant, it goes out, and that's why you have this left now. Okay, we have this, and then we also have summation from I equals 1 to n of um of just yi, because for this other one too, -2 also cancels out, so you just have yi minus mxi plus b, and all of that again is equal to 0. So you have these two now. So that's the second step. Then step 3, the third step is to solve the system of equations. Solve the system of equations. Solve the system of equations. So here, we now have two equations. We have two equations with two unknowns. Two equations with two unknowns. So that's a nice problem. That means we can get a perfect solution to this. So we now have two unknowns, m and b, which we can solve algebraically or numerically. Okay, so with that done, we can move on to take an example. So we have example. So given the following data points, that's 1, 2, 2, 3, and 3, 5. Okay. We want to find the best fitting line, y equals mx plus b. Okay. So of course we go step by step again. For the first step, we define the sum of squared residuals. Of course. All right, so we get back here, and I have to define the sum of squared residual. So J of m comma b equals summation yi minus mxi plus b squared. So since we have squared now, it doesn't make sense to just expand it directly like that. So it's better to just substitute the values. So we have j m comma b equals summation from I equals 1 to n of, oh, okay, no need to do summation again now. So we'll use the values up here. So we now have two equations with two unknowns. Okay, the points are 1, 2, 2, 3, 3, 5. 1, 2, 2, 3, 3, 5. So we have 2 minus xi there. Or I can still take the pain to say this is yi minus mx, y1 minus mx1 plus b plus y2 minus mx2 plus b. Okay, then plus y3 minus mx3 plus b. Okay, all squared. This square thing again. Okay, so what do we have? we have j m comma b now equals, so 1, 2, right? So y1 is 2. So we have 2 minus x1 is 1. So 1 times m plus b all squared. Then um all that, right? Then we have um, I'm wondering if it's important to do this, since if I can just get the expressions directly and use them, then we can be fine, right? Um, okay, okay. Yeah, so let's keep at it. Let's keep at it. Okay, 2 minus m plus b squared, then plus y2. So that's 2, 3. So that's 3 minus x2 is 2. So we have 2m plus b all squared. Then plus 3, 5, I think. So that's 5 minus 3m plus b all squared. Okay. So for all this now, we can then, yeah, so that's the expression we have for this. So 2 minus m plus b all squared plus 3 minus 2m plus b all squared, 5 minus 3m plus b all squared. So this is the key expression we need going forward. Okay, so we can now go to what is now supposed to be step 2. So 2, we set up the normal equation, set up the normal equations, set up the normal equations. So that means we have, so of course we compute the partial derivatives, compute the partial derivatives and set them to 0, and set them to 0. So we start for slope m, for slope m. So this expression we differentiate with respect to m. So we need partial j, partial m. So let's go carefully. Um, so for this part now, our focus is on m. So we have bring down power 2, then differentiate m. You just get 1. Then the minus attached to it is attached to it. So we have minus 2 into 2 minus m. I mean 2 minus m plus b. And then the power is reduced to 1, right? So we have 2 minus m plus b. So the next thing, or another thing we can do is we can just take these formulas directly and substitute. We can do that too. We can do that. Maybe that's even better. But I mean, you have the formula, so you can substitute directly and use that instead of going through this stress again. So the next thing is we are differentiating m here. So again, we bring down power 2. Then now m has a coefficient in this case. So we are going to have 2 times minus 2 for that second part. So that will be this now plus 2 times minus 2 into 3 minus 2m plus b. Okay? So that's 2 times minus 2, 2 times minus 2 into 3 minus 2m plus b. And then the power is reduced by 1 again, like that. Yep, that's 2 into all that. Great. So we have the last part. So we differentiate with respect to m. So we have these two coming down minus 3. So we have again plus the 2 that will come multiplied by minus 3. Okay. The 2 that will come down multiplied by minus 3 into 5 minus 3m plus b. Okay. Yeah. So with that now, I think we are good to go. I think we are good to go now. Of course, in all, we need to equate this to 0. So, but we can tidy it up a little bit more. Now we can see minus 2 is common to everything. So partial j, partial m, minus 2 is common. So we have minus 2 into 2 minus m plus b. Okay. Plus, minus 2 is out already. So we have plus 2 into 3. Okay, let me expand directly so that I don't waste time with that. So let me just expand inside the bracket. So minus 2 is out. Okay, maybe that can be confusing. So let me just leave it. Minus 2 into 2 minus m plus b. Okay. Minus 2 is out, so we have plus 2 into 3. Okay. Maybe what I should do is I can open up the inside at least. So 2 minus m minus b. That'll be helpful at the next stage. Then minus 2 is out, so we have plus 2 into 3 minus 2m plus b. Okay. Then we also have minus 2 out, so we have plus 3 into, because, minus 2 goes out, so we have 3 left into 5 minus 3m minus b. Okay. So minus b, like that, all this. So partial j. So partial j, partial m now is equal to minus 2 into, so we have 2 minus m minus b plus 6 minus 4m. Okay, yeah. Thankfully, I quickly cut this. This should be minus b. So this is minus b here. So 6 minus 4m minus 2b, right? Then plus 15 minus 9m minus 3b, like this. Yeah. 15 minus 9m minus 3b. Yeah, that goes. So some tidying up, partial j, so partial j, partial m is equal to minus 2 into 2 plus 6 plus 15. 2 plus 6 is 8 plus 15, that's 23. Then minus m, so minus m minus 4m, that's minus 5m. Minus 5m plus 9m, that's minus 14m. Then for b minus 3b, minus everything is minus 6b. So now, okay, this is what we have here. We can equate to 0, right? So partial j, partial m equals 0 implies that we now have minus 2 into 23 minus 14m minus 6b is equal to 0. Of course, we can divide through by minus 2, so we just simply have 23 minus 14m minus 6b equals 0. We can tidy things up, and that would be like 23 equals 14m plus 6b. Okay, so we can have 14m plus 6b equals 23. Okay, call that equation star. Okay, call that equation star. So we'll come back for it later. So the next one is for slope b. For this is for m, right? That's for slope m. Then we talk for the y-intercept b. Okay. Yeah. So next for the y for the y-intercept b. So we can go on carefully again. So same expression with differentiate with respect to b. So I guess this is easier. All we just need is minus 2 everywhere. Okay, we have minus 2 everywhere because we're not focused on m. So we can as well just have minus 2 into whatever we already have there each. So maybe I'll go straight this time. So I'll just have partial j, partial b is equal to minus 2 into every other thing you have without the power 2, because we'd have differentiated all that off. So we have minus 2 into 2 minus m plus b. Okay, that is 2 minus m plus b. Then next, yeah, we can have that 2 minus m plus b. Next we have the minus 2 is already out. So we have 3 minus 2m plus b. 3 minus 2m plus b. And then finally 5 minus 3m plus b. Okay, this is pretty easy. We just have it like this. Partial j partial b is equal to minus 2 into 2 minus m minus b plus 3 minus 2m minus b plus 5 minus 3m minus b, like this. So partial j partial b is equal to minus 2 into, okay, we can tidy things up. 2 plus 3 plus 5, that's 10 again. So we have what? Minus m minus 2m minus 3m, that's minus 6m. Then minus b in 3 places, that's minus 3b. Okay, then we can equate to 0. So partial j partial b equals 0 implies that we have minus 2 into 10, all right, minus 6m minus 3b, and that is equal to 0. So doing that, we have 10 minus 6m minus 3b equals 0. That means that 10 is equal to, okay, well, I can do that. 10 equals 6m plus 3b. That means we have 6m plus 3b is equal to 10. And that equation, you can call that equation star star. Okay, so we have the two equations we need to solve now. So that takes us to the next step where we solve the equations. So that's step 3, I believe. That's step 3. Step 3. Solve the equations. Solve the equations. Solve the equations. A little trouble with perfectionism here. Solve the equations, right? Okay. So with this, okay, I've not been writing step for the rest, right? So, okay. All right. So we have two equations basically, and we need to solve for m and b. So 14m plus 6b equals 23. 14m. Now we have 14m plus 6b equals 23. And then what else? We have 6m plus 3b equals 10. 6m plus 3b equals 10. So from what that looks like, this is equation star again. This is equation star star. So we now need to solve for m and b. So from what I can already see, I see 6b, I see 3b. So it's easy to take care of b first. So equation star times 1, we have 14m plus 6b equals 23. Now what I mean to do is I multiply equation star star by 2, so it can become 6b. So 6 times 6, that's 12m. 3 times 2 is 6b. 10 times 2 is 20. So with this now, it's easy to eliminate b. So we can subtract, so we can just, subtracting, we have 14m minus 2m, that's 2m, minus 12m is 2m, 6b cancels. So 23 minus 20 is 3, okay? 23 minus 20 is 3. So that means that m is equal to 3 over 2. And that means the intercept is 1.5. So easy peasy, we have that sorted. Then we have 1.50 if you like. Then next, since we have m already, it's easy to get whatever else we need to get. So we can just say from equation star star now. From, okay, let me preserve this for later. Okay, let me say from equation star star, which is the simpler of the two. We can use any of the two equations actually. So 6m plus 3b equals 10. 6m plus 6m plus 3b equals 10, right? That's what we have there. 6m plus 6, 3b equals 10. And m is 3 over 2. So we have 6 into 3 over 2 plus 3b equals 10. Okay, so 6 here is 1, 6 here is 3. So 3 times 3 is 9 plus 3b equals 10. So we have 3b equals 10 minus 9, and then 3b equals 1. So b is 1 over 3, or you can say 0.33. Okay, so that gives us a very sweet answer right there. So we have our m and b. So our fit is ready. Our fit is ready. So we can then say, therefore, the so thus, okay, I'm using therefore and thus together. That always happens. But then it's better to say thus the best fitting line, is y equals 1.50x plus 0.33. So that is what works for that. So well, I mean, in conclusion, the least squares method successfully finds the best fitting line, y equals 1.50x plus 0.33, which minimizes. So we can now say this, okay, this, uh, yep. So this, this minimizes the sum of squared residuals, the sum of squared residuals between the observed, between the observed data points, between the observed data points and the predicted values, and the predicted values. I mean, for the sake of, I always like to show you the Python implementation. So if you look at the Python implementation, this is what that looks like. So you declare the points you need, and then the linear fitting is there. So you declare the fit in line 10, and then then we visualize, and the equation is also displayed in line 22. So if I run that, this is what we get. So you see the equation, what we just got now. So I mean, the Python thing is also important because you can now extend. You can now maybe say you're extending to 4, and that automatically. So you don't, if you have to calculate that manually, that's a lot of stress, right? So with 4 now, it has changed to 0.80, 1.5. So you can go ahead, you can keep going. You can even say maybe you need 9, maybe 917. So 917. So the values also change. So so the Python code is there for you to extend for as long as you want. You can have so many data points. For using this, something is wrong. What did I do wrong? Okay, this 4 should also go. Okay, so now we have this. Yeah, so this has been a very long video. I didn't intend that it should be this, but if I can cut that part out, maybe I will. If not, I'll just leave it this way. So before I go, I won't hesitate to give you a practice question. Practice question. So obtain the best fitting line. Obtain the best fitting line for 2, 1, 3, 2, 4, 7. Say 4, 7, then 7, 10. Okay, obtain the best fitting line for that, right? Then so you're going to end up getting y and all that, right? So add to the question, find y when x is equal to 0.325. Okay, so feel free to put your answer in the comment section, whether on Facebook or YouTube or wherever you find this. And then after that, Of course, if you have subscribed, thank you so much for doing that already. If you have not, please go ahead and subscribe right now. Hit the notification bell so you can always get alerted each time a new video is released. Comment your answers to this problem. Let me see. Then let me also know if you have a problem you'd like me to solve, a topic you'd like me to teach. You should also go ahead and like and share so that more people can have access to this great content. So, like, come your way again. Keep doing maths right. Bye.